Okay, so this is the first problem on chapter 7.4 where we're looking at rotational dynamics. So that means we'll have rotational kinematics and we will include, forces. Okay, so anyway, so we got a 0.10 kilogram solid rubber ball. And it's attached to the end of a 0.80 meter length of light thread. Okay, so that is the radius of this particular circle. We will note that the reason that they mentioned that the thread is light is that we don't want to worry about the mass of the thread. At this point, you guys wouldn't know how to deal with the mass of the thread just yet, so I wouldn't stress that too much. The ball is swung in a vertical circle. The speed of the ball is kept constant at 6.0 meters per second throughout this experiment. Okay, so that particular speed is tangential. So it is customary. A lot of times people will write a 6.0, a little sub t for the tangential velocity. I'm going to not leave it on there. I'm going to take it off because that's the only velocity that we're going to have. Okay, so we'll just call it v. Okay, determine the tension of the thread at the top of the circle and at the bottom of the circle. All right, so this is the first time we have tackled anything like this. So it's important to consider the fact that normally when we deal with forces, we do go in the x and the y direction. And in this particular case, we will not be going in the x and the y. And you might be looking at this particular diagram and you might be thinking, well, why not the x and the y? I mean, it would work in x and y for this particular case. And the reason that the reason that I chose this one as a warm-up is that it's a little bit easier. And I wanted to demonstrate that we are going to be going in the r and the t direction, so the radial and the tangential direction. Okay, so, and there is a very good reason for that. Right now, the most important thing is that you just learn it, and then we'll talk about why we're going to do what we're going to do when we do it. Okay, so the r direction at all times is always going to be, so, like when it's at the top, or when it's at the bottom, or when it's on the side, or whatever, it doesn't matter where it is. The r direction is the radial direction, so that is always outwards. Okay, so I'm going to draw it on the top. It's going to be straight up, so that means out away from the center. So that will be our r direction. Okay, and then on the bottom, the radial direction is going to be out, and that is going to be downwards. So that is going to be, again, away from the center. Okay, the tangential direction, by convention, is always tangent to the circle, so it is at a right angle to the r direction, and it is always, by convention, going counterclockwise. So that may take a little bit more thinking, but what I recommend you do, if you can't picture a clock, is you put your right hand such that the thumb is sticking up from the center of the circle. And you can see which way your fingers are pointing, and if you do that, you'll see that at the top, it's going to the right, to the left, and at the bottom, if you continue around that circle, it will be going to the right. Okay, so if you do that, this just kind of like, we're just kind of doing this, on this particular circle because it's visible, but I'll show you a few more spots. I'll show you the left end of this circle and the right end of the circle, and remember that r is going to be outwards, okay, always. And the tangential direction is going to be making, a counterclockwise circle. Okay, so it's it's weird. I mean, there's just no way around it. It's going to take a little bit of time to get used to. Okay, so the sooner you get into it, the better. All right, so once we have done that, it doesn't really matter. I was just kind of like showing you how to do that on this particular picture. But what I want to do is I want to consider these two locations individually. So if we're going to go over here, and I'm going to start with this location at the top of the circle. So at the top of the circle, this is a Newton's law problem, okay, because we're looking for tensions. So we need the tension as a force, right? So at the top, we need to draw our system, which is going to be a dot, okay, the rubber ball. And then I will draw the radial direction, which is out from the center. And then the tangential direction, which is counterclockwise, which in this case is to the left, okay? So once we are there, all we have to do is we have to identify the forces on this particular ball. So at the top, well, we've got tension, which is pulling downwards, okay, because that's the way the rope is attaching. Ropes can't push. And then we've got the force of gravity, which is always downwards, okay? Once we have those two forces, we have a completed free body diagram because we got the system, the geometry, and the forces, and we don't draw anything else. So now that we're here, we're going to do the sum of the forces equals ma. Now, normally we would do the x direction or the y direction, but in this case, there's no x or y direction. There's r direction and the t direction. And I think you'll notice that there's nothing going on in the t direction. So we will sum of the forces in the r direction. Okay, so let's see. What do we have in the r direction? Well, t and f sub g are both in the negative r direction. So I'll expand the left-hand side of that equation to be negative t minus the force of gravity equals, and I will leave that right-hand side alone for now, m-a-r. Okay, so now we're going to keep going, and let's see. This is the next step is always to expand, so we'll do negative t minus f sub g becomes mg equals. Okay, now the right-hand side here is actually the easy. This is the easiest. It's very hard to think about, but it's easy because it's maybe the first and only time in this class where I will give you an always. The radial acceleration is always towards the center, which means it's always negative. And then it is always, magnitude-wise, it is always one of two quantities. It is either v squared on r, or it is r omega squared. It just depends which one they give. I guess it could also be a sub c, but people never give you the a sub c. So that just stands for centripetal acceleration. Okay, all three of those are equivalent. You may use either one or any of them. I recommend v. For this particular problem, v is given, so we're going to go with v squared on r. Okay, once you're there, okay, this is just some algebra, right? So we'll do a little storm L on that, and we will just rearrange it. Okay, so let's see. So that's going to give us t equals m v squared on r minus g. Okay, I will note that mv squared on r is sometimes called the centrifugal force. It is not a real force. It is a imaginary force. It is just it is essentially the how much you have to accelerate this object, essentially, in order to get it to go around that circle. Okay, so if we plug and chug, we are going to end up with a tension of 3.519 newtons. And because we want 2 sig figs, we will call that 3.5 newtons. Okay, we'll box that and we'll move on with our lives. Okay, now we're going to do the exact same procedure, but we're going to do it on the bottom. So let's see, at the bottom, let's see, so we're going to have a free body diagram again. So again, the system is just a dot, and we are going to, let's see, okay, so we need the radial direction. So we're at the bottom, so the radial direction is out from the center. So if you're at the bottom, that means the radial direction is down. And the tangential direction, if you're at the bottom, because we're going counterclockwise, is going to be to the right. Okay, so we'll put a little t right there. All right, now we need the forces. Let's see. So there's a rope attached to this thing. The rope is pulling it upwards. So that's the tension. And then there's a force of gravity. And so the force of gravity always goes downwards. Okay? So again, now that we've got a full free body diagram, because we've got the system, the geometry, and the forces, so the next step is to sum forces. Okay? Once again, there's no reason to go in the tangential direction because nothing's going on in the tangential direction. So we'll go in the radial direction. And what we'll do is we will, well, let's see, in the r direction, t is going in the opposite of the r direction. So this is a little bit confusing because r is downwards and we want down to be negative. But in this case, we've drawn r out because that's the correct way to do it. But out is down, so therefore t, which is in the opposite of the r direction, gets a negative sign, whereas gravity, which is in the positive r direction, gets a positive sign. So that's a little bit weird. So, wrap your brain around that a little bit, that gravity, because it's in the positive r direction, gets a positive sign. T, which is in the negative r direction, gets a negative sign. Okay, equals, we're going to leave m-a-r, we're going to leave that all alone. We leave the right-hand side for the first step all alone, and then we'll go negative t plus, we'll expand f sub g into mg equals, let's see here, m, and again, like I said, this is the beauty of it. A sub r is always negative. It's either r omega squared or v squared on r, v squared on r for this one, and we'll draw a little storm L on that. Okay, if you can get that, you've got the physics. Okay, the rest is just algebra, so we'll say t equals m, let's see, v squared on r plus g. Okay, notice it's the same answer as we had earlier, except g has flipped signs. Okay, because earlier the gravity was helping this thing turn inwards, and in this case, gravity is fighting the turn inwards. All right, so if we're going to plug and chug, we're going to get a T of 5.481 newtons, and if we round to sig figs, we'll get 5.5 newtons. Okay, that's it. So hopefully this was helpful, and I will, take care of yourselves. It's going to be a cold one tonight. So always remember, physics is important, but the rest of your life is more important. All right, hope you guys take care. Bye.